Okay, so welcome everyone, a few minutes later than the last one, to another conference. This is going to be, I think, the third one out of 5 that we agreed to do before spring break. And this is looking at balancing chemical equations and molecular equations, ionic equations, and net ionic equations. Okay. I don't know if anyone's going to be here for this one. Again, it was very short notice. I apologize for that. I can do them when I can do them, and I know I could do it right now. Sorry, it was the chair of the department asking something. So let's get going with some balancing equations. And if anyone does show up, if you could just give me a heads up on the chat system, whether you can hear or see me. I think I've hit all the right buttons, but I don't know until you let me know. Okay, so when we balance chemical equations, balancing equations. So what is it and why do we do it? We're doing it because we have to obey the conservation of mass law. We have to obey conservation of mass, which basically says mass or matter. So although matter and mass are not the same thing, we can use them interchangeably because matter has mass. So matter can neither be created nor destroyed, but rather converted between forms. We can't create or destroy matter, but we can reassemble matter with other forms of matter to form new individual things. Okay. So when we balance equations, we're obeying this, obeying the conservation of mass law. You should probably have a little read about the conservation of mass law. So it's accredited to Antoine Lavoisier. Unfortunate guy, got guillotined in the French Revolution, but not before he started chemistry. So he is considered one of the fathers of the subject. So around the revolutionary years, late 1700s. So that's what we're doing. So I would, have a little dig around, see who Antoine was, and that type of thing. Okay. So I'm going to erase this, and then we'll look at some examples of how you'd actually do it. Okay, so let's start with something simple. Let's say we have nitrogen and hydrogen. Nitrogen and hydrogen are going to give ammonia. Okay. So we have to obey the conservation of mass law. Right now, as it stands, we have 2 nitrogens, because the 2 means I've got 2 of them. I've got 2 hydrogens. And on the right of the arrow, I only have 1 nitrogen, where I have 3 hydrogens. So right now, they're not balanced. We can treat the arrow as an equal sign. So somehow I've lost a nitrogen and I've gained a hydrogen. So this is not a balanced equation. I'm not allowed to change the subscripts because the subscript is a part of the chemical. I'm not allowed to do that. What I can do, I can put numbers, coefficients in front of the chemical. I can basically Xerox the chemical and make a copy of it. So it doesn't really matter where you start. It doesn't really matter where you start. So pick anywhere. I'm going to start here. There's no right and wrong way to start. I have 2 nitrogen on the left. So I need to put a coefficient 2 here because I need 2 nitrogen on the right. That coefficient now multiplies everything. So I've got 2 nitrogen, or I've got 2 multiplied by 3, I've got 6 hydrogen. There's 6 hydrogen. So I have to come back over to this side, and I have to put a 3 here, so that the 3 will multiply the 2 and also give me 6 hydrogen. Now we can see that we have 2 nitrogen and 6 hydrogen on each side. Indeed, we're obeying the conservation of mass law. So by the addition of this coefficient, we now know it's a 1 mole, 3 mole, 2 mole ratio. These numbers we could then use in mole type calculation. These numbers you can see are coming from balancing the equation. What we're saying when we balance is that this mass is equal to that mass. So we're conserving mass. Whatever mass goes in has to go out. Notice we are not saying that 4 moles equals 2 moles. There's no such thing as balancing moles. Sorry. There's no such thing as conservation of mole law. We convert the mass into moles, but we are balancing the mass. We're not balancing moles. Okay. So again, if anyone has a question, if you just send a little chat, I'll see it. My computer will ding and I'll stop. But I'm just going to continue then. What about excuse me, something a bit more exotic like this? KClO3. This, for what it's worth, the name of it, this would be potassium. Well, in the previous video, we said something with oxygen ends in 8. So chlorine and 8, so it's chlorate. This is potassium chloride. So potassium chlorate becomes potassium chloride plus oxygen. Right now, I have a potassium, I have 1 chlorine, and I have 3 oxygen. And on the right of the arrow, I have 1 potassium, only 1 chlorine, and I've got 2 oxygen. So right now they're not balanced. Doesn't matter where you start to balance the equation. I have 1, so I'm going to start here, just randomly. I have 1 potassium on each side. So it seems like everything's okay except my oxygen, right? So I can't change this 3. I can't change that 2. But the way I would do it, there's more than one way to do it, but the way I would do it, I would say, okay, how do I make 2 into 3? I'm going to multiply it by 1.5. So 1.5 multiplied by 2 is 3. Problem is, it looks ugly. So although it's right, I've obeyed the conservation of mass law, it's stylistically it's stylistically ugly to have a decimal in your final value. So what we do when we get something like this, we multiply through to get rid of the decimal. So if I multiply everything, both sides of the arrow, by 2, I can get rid of that decimal. So this 1 becomes a 2, this 1 becomes a 2, and this 1.5 becomes a 3. It's still balanced. So now I have 6 oxygens. 3 multiplied by 2. I have 2 potassium and 2 Cl on each side. So we're still balanced, but stylistically it looks a bit better. Okay. So we would use 2 moles, 2 moles, 3 moles. This is the way you should do it. Now, let's say you didn't do it that way. Let's say you just had what I previously had and I told you it was ugly. Let's say you divided everything by 2. Well, it's best to do it that way. If you had it the uglier way, it would still be correct. You'd still proportionally have the same stuff. 1 mole to 1 mole to 1.5 mole. It's ugly, but it's not wrong. But again, you want to avoid having decimals. Okay, so again, if there's any questions, just send me a message and I'll pause and answer your question. And again, while I think on, I've just posted to the Canvas site a worksheet that I owed you to give you a chance to gain points for balance and equations. So if you're watching this video, I recommend that you, after this and you're ready, you immediately do that, get it out the way and get it in your outbox instead of your inbox. Okay, let's try ramp it up to something a bit more, maybe a bit more challenging. Okay, so this is a little bit more complex, but still the same idea. I'm not too worried about you naming acids, but for the sake of naming it, this is sulfuric acid. The same acid that you'd find in a car battery. This is sodium nitrite. And again, you can find a wealth of worksheets and answers already made on the internet, in addition to what's in your textbook. This would be nitrous acid, and this is sodium sulfate. Notice there's not a prefix in sight because sodium, and hydrogen are all in the S block. We can predict their charge. There's no need for any prefixes. There's no need for any stock notation. Okay, but right now it's not balanced. Now this example has polyatomic ions in for the first time. Now there's 2 ways you can treat polyatomic ions. You can either keep them together, or you can look at the individual atoms separately. It doesn't matter. Okay, doesn't matter where you start. So let's inspect. On the left of the arrow, we have 2 hydrogens. But on the right of the arrow, we only have 1 hydrogen. So I'm going to put a coefficient 2 here. So now I've got 2 hydrogens on each side. This coefficient 2 multiplies the NO2. So I've got 2 nitrites. On the left of the arrow, however, I've still only got 1. So I go back and I put a 2 here. So now I've got 2 nitrites. There's no need to put the nitrite in parentheses. Remember, within a molecule of NaNO2, there's only 1. So I've just got 2 copies of 1. So there's no parenthesis here. I've got two sodium on each side, that's good. And I've got one sulfate on each side. So if you look at this, I have, well, pointing it's easier. I have two hydrogen on each side, one SO4, one sulfate on each side, two sodiums on each side, and two nitrites, two NO2s on each side. So this is balanced in a 1 to 2 to 2 to 1 mole ratio. Okay, I'm just going to check, see if anyone's asking a question. It should ping and alert me. Okay. I'll assume I'm good to go. All right, unless there's any questions, I'm going to erase this and look at another example. Another couple of examples, and then we'll start looking at molecular ionic and net ionic equations. Okay, what about something like this? C3H8 plus O2 gives CO2 and H2O. This is an organic molecule, so it's something we don't really have to worry about naming in Chem 65. But for the sake of giving it a name, this is propane. Propane and oxygen is carbon dioxide, one carbon and two oxygens, and water or dihydrogen monoxide. Okay, so this is just oxygen. Okay. Doesn't matter where you start, so start somewhere. You have 3 carbons on the left. You only have 1 carbon on the right, so you put a 3 here. You have 8 hydrogens on the left. You only have 2 here. So a coefficient form multiplies the 2, so you have 8 on both sides. This 3 impacted that oxygen. So you actually have 6 oxygen plus 4 over here, so you have 10 oxygen total on the right. So we have to go back and put a coefficient 5 here to give 10 oxygen on the left also. So this would exist if you reacted it in a 1 to 5 to 3 to 4 mole ratio. In addition to not having decimals, if ever you had a situation where you could reduce it down, you would always do so. For example, if you had a 2 to 10 to 6 to 8, you would always reduce that down, even though you would still be able to use it in a calculation and get the right answer. You would just present it in its most reduced form by dividing by 2. If you can divide and reduce down, always do so. That's merely for style reasons. Okay, similar to this example, I think next we'll look at photosynthesis. So photosynthesis is a chemical reaction that you will probably encounter for the first time in a biology class. Probably familiar to you from, the case system, if from nowhere else. So what if we had glucose, so C6H12O6, that's glucose. So we have food. So actually, this is cellular respiration, not photosynthesis. Cellular respiration, we have glucose. Well, we need to breathe some oxygen, and then we have our exhaust gases. Let's balance cellular respiration. You have 6 carbons on the left, so we need to put a coefficient 6 here. You have 12 hydrogens on the left. I have 6 over here, so let's put, sorry, I have 2 over here, so let's put 6. So 12 hydrogens on either side. I have 12 oxygens here, and I have 6 here, so I have 18 oxygens total over here. I already have 6, so I need an extra 12, so let's put 6 here. So now I have 18 oxygens on both sides. So cellular respiration, for every mole of glucose that you consume, that you metabolize, you actually need 6 moles of oxygen. You'll produce 6 moles of CO2 in your breath, along with 6 moles of water. So we can balance cellular respiration. The opposite of cellular respiration would be photosynthesis. So let's balance photosynthesis. So photosynthesis is almost this in reverse. So a plant will take carbon dioxide from the atmosphere, gaseous CO2, and you have to water the plant, give it some water, and with the energy of sunlight, it will construct glucose and give us oxygen to breathe. So photosynthesis is the opposite of cellular respiration. So plants do one thing, animals do the other. How convenient. We can just look by analogy. We know that that's going to be 6, 6, 6. So for the same reasons it was balanced here, all we've done is flip it around. We haven't changed anything. There's some relevant biology examples. Okay, so let's move on a little bit. Spend the last half of the hour looking at molecular ionic and net ionic equations. They come in threes. So we're going to look at one equation in its molecular form, its ionic form, and its net ionic form. Okay, so they come in threes. So typically, well, everything we've been looking at so far has been molecular. So if you don't see any charges exposed, assume it's a molecular equation. So for example, ACl, AQ means aqueous, it means it's dissolved in water, plus lead nitrate, aqueous, gives potassium nitrate, aqueous, plus lead chloride, or lead 2 chloride. So this is a molecular equation because there are no exposed charges. So as you can see, we've just been looking at molecular equations. Notice I've added the state that the chemical's in. So if I write S, you know it's a solid. If I write G, you know it's a gas. If I write L, you know it's a liquid. And if I write AQ, it's aqueous. That means dissolved in water. It's important that you write this extra information when you do this type of thing. You don't have to memorize what state they're in. It will be provided to you, but when it is provided to you, you have to use it. You have to use it to get the ionic equation. The ionic equation, you take only the aqueous species and you separate them into anions and cations. So I know from looking at the periodic table, so in the previous video we predicted charge, I know that we're going to have K with a single plus aqueous. We're going to have Cl with a single minus aqueous. So again, I go from the compound or the molecule to the ionic form by just separating the anion and cation. Likewise, I have lead. Now, lead can have more than one charge. All right, I'm just going to text my wife, otherwise she'll keep calling me. Actually, I'm going to answer her. Sorry, 1 second. Hey, I'm recording a video. Can I call you back? I've got a rideshare. Yeah. My wife was panicking about picking my son up from school, but I've got it covered like a good daddy does. Okay. We know, because we've memorized from a list of polyatomic ions, that nitrate has one negative charge. And I've got two nitrates. So what would satisfy two negative charges? Well, it has to be two positive charges. So based on knowledge of a known, you can predict something that has a variety of options. You can predict which option it has. Two nitrates. Okay, so we've separated the aqueous species into its ions. Here again, we have K plus and NO3 minus. But this species here is solid. You can only separate aqueous. So we just have to leave that alone. That would just transfer as is. It wouldn't form ions. The net ionic equation, you look at your ionic equation and you cancel any species that looks identical on both sides. So we notice on the left we have K plus. We have exactly the same thing on the right, so we cancel them. These are called spectator ions. We have one thing I didn't do, because I'm a bad chemist, I forgot to balance the original molecular equation. So had I done that, because this will affect our calculation, so that's very bad. I really should have had a 2 here and a 2 here. So we cancel 2 potassiums, not just 1. We now, because of that 2, we now have 2 nitrates on each side of the arrow. So the only thing that won't cancel is the lead and the chloride, because it's trapped as a solid over here. You can't cancel over here, so you rewrite what's left. So we have, right, and because of that 2, that should have been 2, right? I'm sorry, that should have been 2. So I have 2 Cl minus and lead 2 plus. Everything's canceled except the arrow and then the solid from before. That's our net ionic equation. So you'd be expected in Chem 65 to be given a molecular to write the ionic and then the net ionic. Notice that the net ionic looks much more simple than the molecular. And it's important that a chemist can do this because, for example, here she would then realize that the potassium has no effect on the reaction because it doesn't survive the scrutiny to get to the net ionic. So there's no point trying to tweak the potassium conditions. So we get rid of what's not important and we focus on what is important. Okay, so I'm going to do another example, and this time I'll remember to balance it ahead of time. Okay, what about Na2CO3 FeCl2 gives FeCO3 and this time I remembered it should be balanced. So we have sodium carbonate, iron 2 chloride. Iron is our first D block metal. D block almost always requires stock notation. We give iron 2 carbonate and sodium chloride. Okay. This clearly is a molecular equation because there are no exposed ions. So this is molecular. So let's now write the ionic. Oh, sorry, I've just seen a question. Sorry, Deirdre, I didn't realize you asked the question. Can you explain the difference between balancing the equations versus the work you did in the previous video? Simply predictions. Okay, so very good. So I last saw your question. The previous video was predicting the ratio of ions in an ionic compound. The previous video obtained these subscripts. So these subscripts, the reason why, for example, that's a 2 to, well, that's not a subscript, remember, carbonate is a polyatomic ion, so that's one chunk. So this 2 to 1 ratio, this 1 to 2 ratio, predicting the composition of single species, that was the previous video. Now we're looking at the ratio between species, not within a species, but between species. I don't know if that, I hope that answers you, I think that answers your question. So we need to do both. So typically, if I'm going to ask you to balance an equation, I'm not going to ask you to, if I'm going to ask you to do this, I won't ask you to predict the ratios as well. Because what if you get one of them wrong, then you get the whole thing wrong. So I'm either going to ask you to predict the ratio, as in the previous video, or I'm going to ask you to balance the equation, like in this video. Both of them are related and needed to do basic chemistry. If I didn't answer your question, rephrase it, but I'm gonna move on because I think I did, and I'm sorry it took me so long to realize you asked. Okay, so ionic, we have to separate the anything that's aqueous. So I have 2 sodiums. I know from the previous video that it has a +1 charge, and I know from the subscript here that there's 2 of them. Carbonate, I've memorized as a polyatomic ion is CO3 2-. If you don't know that, that would be a problem. Iron 2 chloride, from knowledge of chloride, I know that iron must be iron 2 because it's the only thing that would cancel the 2 negative charges here. I've got 2 singly charged chlorides. The solid, I can just write it as is. I can't separate it because it only aqueous substances can be separated. And I've got 2 sodiums and 2 chlorides. Okay, so that's my ionic equation. Again, I've separated all the aqueous species. Get the net ionic, I have to cancel spectator ions. For anything that looks identical, so you have sodium on each side, you have 2 Cl minuses on each side. So what remains is carbonate and ion 2 give ion 2 carbonate. Much more simple than this, and this is the only thing that's important. So I'm going to wait a second, see if there's any questions. I'm going to get out of the way of the camera because that would be useful. Okay. So look at a couple more examples, and I recall from last semester, I think there's some labs coming up, or a lab coming up where we'll look at this as well. I'm not exactly sure. Okay. So here or seeing there are no questions, I'm going to erase this and we'll look at another example. Okay. Again, you can Google, practice net ionic equations, and a gajillion examples will come up with answers. That's where I got this example from, just looking for examples online. They're already answered for you. So you can practice those, and let me know if there's any issues moving forward. Okay. How about this one? And again, remember, I don't expect Chem 65 students to know if something will or won't dissolve in water. You'll be told if it's aqueous or not. You just have to then react to that information. So here we have an equation, it's balanced. There's no exposed charges, so it must be the molecular equation. Let's convert it to an ionic equation and then a net ionic equation. We separate ionic charges. Magnesium, from the previous video, we know is in group 2. Anything in group 2 must form a +2 charge. This is magnesium 2+. I have parentheses and OH inside it, so I know OH is a polyatomic anion, and there's 2 of them. There's 2 OHs. What's the charge? Well, there are 2 of them to satiate 1 Mg2+, so they must each be negatively charged, and that's why there's 2 of them. I've got 2 H pluses and 2 Cl minuses. On the right of the arrow, I have Mg2+ and 2 Cl minuses. Again, the subscript becomes a coefficient in reverse of what we did last video. Liquids, gases, solids can't be broken up, so we just write them as is. Again, the only thing that you can make ionic is something that's aqueous. Okay, we now cancel spectators. Well, I have a magnesium cation on both sides. I have 2 chlorides on both sides. So I can't cancel anything else, so I just rewrite what's left. 2OH minus and 2H plus give 2H2O. Now this is almost finished. Everything is a 2. So although it's okay, it needs to be polished. So you would just divide through by 2 to reduce down to its lowest common denominator. So this is a 1-to-1 ratio. So as you can see, this looks complicated, but this chemical was completely irrelevant. Because it doesn't appear anywhere in the net ionic equation. So what was the product here? Really, this was the only product. Even though we had magnesium chloride, it was nothing. We're making water. We're making water in a fancy way. So again, the net ionic equation forces you to focus on what's really happening and not get sidetracked with chaperones. Okay. So this chemical would be magnesium hydroxide. Here we have hydrochloric acid. This is the same acid that's in your stomach acid. I'll name the irrelevant product. This is magnesium chloride. We have water or dihydrogen monoxide. Okay, we have about 10 minutes left. So definitely time to do another example, and I have a nice different type of example in mind. So if there is a question with this, now is a good time, otherwise I'll erase and we'll do what's going to be probably our last example. Okay. Okay, so our last example, we'll write down the molecular. What if we had this equation here? Make sure it's balanced, so I need a 2 here, counteract that 2. I need a 2 here to counteract that 2. So we have a balanced molecular equation. We have sodium iodide. We have potassium carbonate. Sorry if most of this video is looking at the back of my head. That's what I have to do if I write on the board though. Potassium iodide and sodium carbonate. Okay. Let's write the ionic equation. Got two positively charged sodiums and two negatively charged iodides. I've got two positively charged potassiums, one -2 charged carbonate, and that gives two positively charged potassiums, two negatively charged iodides, two positively charged sodiums, and one -2 charged carbonate. I'm now going to cancel spectators and look at the net ionic equation. Anything that's identical can be cancelled. So I have two sodiums on each side. I have a carbonate on each side. I have two potassiums on each side, and I have two iodides on each side. So here we have no net ionic equation. So this just means there's no reaction. So there's a predictive power here. We predicted that this is not real chemistry. All we have is a mixture of ions in a beaker that do nothing. So sometimes you can write something that's not real. One of the ways that you know it's real, one of the ways, not the only way, but one of the tests for a real chemical equation is it must have a net ionic equation. Here we have none. This is not something that exists. This is a bag of ions that do nothing. So a way to spot this, you just look at your products. You must either have a gas or a liquid or a solid. You must have at least one of those for there to be a net ionic equation. Here we just had two aqueous products. Well, they separate and they will cancel the two aqueous product reactants over here. Okay. So we have about 5 minutes left. I don't know if there's any questions or something of that nature. I can't think of any other examples other than the ones I've given that are different. So before we close, are there any questions? Okay, so the question was for these problems, molecular equations will be given, will they be balanced or will we balance them? Typically, if I want you to do this, typically in an exam, you only ask the student to do one thing. So, you know, if I put a question on the exam, what am I asking? Am I asking you to do balance and predict and do this? The danger of doing that is if the student gets one part wrong, they tend to get the whole thing wrong. So exam questions tend to be very binary. There's usually one thing being tested. So If I'm asking you, can you write the net ionic equation, I will balance it for you. So I don't imagine I would ever ask you to balance and do this. So if I ask you to balance, that's all I'll ask you to do. If I ask you to do this, I'll balance it for you. But I'm not gonna give you a compound problem where you've got to do a range of things, because then it sets you up to get one wrong and get the whole thing wrong. So assume that I will balance this for you. Having said that, it's good practice to always check anyway. So I'm telling you I'll balance it, but you should always check anyway. Make sure it's balanced. Any other questions before we close? Okay, so I still owe before spring break, I owe 2 more conferences. I'm gonna look at my schedule. There is a chance I'll do another one today, and I apologize, it's very short notice. But like everyone else with work, family, and I'm going to San Francisco for a conference, I'm looking at slots I can stick this in. So if I can do another one today, I'll announce it, and I won't be able to give much notice. If for some reason you can't look at it live because you didn't have a chance to schedule it in, you can look at the video, and then any questions that come up, put them in the Gibbs Worry discussion forum, and then I'll look at them while I'm in San Francisco. Okay, so again, I might be able to do another video today. It'll be the 4th video. Okay, so seeing no more questions, I'm going to close down this conference.